In this video, we will extend our application of stoichiometry and the molar mass equation to limiting reactant scenarios, which are situations in which we are given the starting quantities of more than one reactant, and we have to determine which reactant will run out first, or in other words, which reactant is the limiting reactant. We're going to discuss excess reactants versus limiting reactants using the combustion of hydrogen in the presence of oxygen to produce water, one of the simplest chemical reactions known, and this chemical equation representing that combustion reaction is balanced at the moment. And we're going to take a mole interpretation of this equation. A mole interpretation of this equation says that 2 moles of hydrogen will react with 1 mole of oxygen to produce 2 moles of water. Of course, we won't always start with 2 moles of hydrogen. We might actually, for example, start with 4 moles of hydrogen, in which case the mole interpretation would say that we would now require 2 moles of oxygen and that we would actually produce 4 moles of water. If we were to start with 10 moles of hydrogen, we would require 5 moles of oxygen and we would produce 10 moles of water. Now these numbers here, the 2, the 4 and the 10, and the 1, the 2 and the 5, and the 2, the 4 and the 10, are in the same ratio as the stoichiometric coefficients. What happens when we're not in the same ratio as the stoichiometric coefficients? For example, if we started with 10 moles of hydrogen and had 7 moles of oxygen, how many moles of water would be produced? We can represent that scenario using these diagrams here. Before the reaction, we can say that we've got 10 moles of hydrogen, represented, for example, by these 10 hydrogen molecules in white here, and we have 7 moles of oxygen, represented by these 7 molecules of water. 7 molecules of O2. What actually happens after the reaction, we still get our 10 moles of water produced, but what we've got are 2 moles of oxygen left over. Oxygen in this case is said to be in excess, and hydrogen is said to be the limiting reactant. It's the reactant that's completely consumed. Once the hydrogen runs out, the reaction cannot continue because there's no more fuel for this combustion reaction, and any excess oxygen will just remain unreacted. It's important we identify which reactant is going to run out, or which reactant is the limiting reactant, because the moles of product, in this case water, the moles of water will always be determined by the moles of the limiting reactant, in this case hydrogen. So our 10 moles of hydrogen plus our 7 moles of water, our 7 moles of oxygen will produce our 10 moles of water. And that's because the oxygen was considered to be in excess, the limiting reactant being hydrogen, and the moles of product are therefore determined by the starting moles of hydrogen. Let's change the scenario slightly. What if we started with 10 moles of hydrogen again, but this time we only had 3 moles of oxygen? How many moles of water would be produced? Well, we can represent that scenario again. Here's our 10 moles of hydrogen being represented by these 10 hydrogen molecules. Here's our 3 moles of oxygen being represented by these 3 molecules of oxygen. And what we find is that there's only enough oxygen atoms to be able to produce 6 water molecules. And so the 6 moles of water that's produced, we get 4 moles of hydrogen gas left over. So in this case, hydrogen is said to be in excess and oxygen is said to be the limiting reactant. It's the reactant that has run out first, and even though there is hydrogen still available for combustion, it cannot combust because there's no oxygen to react with it. And again, it's important to identify what the limiting reactant is, because the moles of product will always be determined by the moles of the limiting reactant. So in this new scenario, we started with our 10 moles of hydrogen. We only had 3 moles of oxygen, and then that only produced 6 moles of water. Mathematically, we can represent that by saying that the moles of water, that's the moles of product, equals 2 on 1 times the starting moles of oxygen. 2 on 1 comes from the ratio of the stoichiometric coefficients. The stoichiometric coefficient of the substance we are trying to find information about divided by the stoichiometric coefficient of the substance we've been given information about. But this time the substance is the limiting reactant, oxygen, where we started with 3 moles. So 2 on 1 times 3 moles gives us our 6 moles of water. So if we look at a scenario that we looked at in the previous video, we were given 5.78 grams of butane and we had an excess of oxygen, and we were asked to find the mass of carbon dioxide in this chemical reaction for the combustion of butane. And what we actually found under those conditions, when we were given 5.78 grams of butane, we produced 17.5 grams of carbon dioxide. You've got to remember, in that scenario, oxygen was said to be in excess, and so therefore butane was the limiting reactant. So the moles, and therefore the mass of carbon dioxide produced, was determined by the starting moles and the starting mass of butane. What about we present a new scenario where we're given 5.78 grams of butane, and this time we're only given 15 grams of oxygen. So the question is, how many grams or what mass of carbon dioxide would be produced? Now, in this case, both reactants have a limited supply. We've got 5.78 grams of butane and we've got 15 grams of oxygen. One of them is going to run out first. The question is which one? And it's important that we identify which one is going to run out first, because it will be the limiting reactant, and the moles of carbon dioxide, the moles of product in this case, will always be determined by the starting moles of the limiting reactant. Now you can look at this 15 grams of oxygen and you think, well, that's significantly bigger than the 5.78 grams of butane, so perhaps oxygen is still present in excess here. The problem with that type of thinking is that you cannot look at the mass quantities and determine this directly. You'll recall that in doing these types of stoichiometric calculations, we first have to convert the mass of substances in step 1 to the moles of substances, and then we have to proceed through and work out the mole of your product, and then in step 3 the mass of your product. So we can't look directly at these masses here and work out which one is the limiting reactant straight away. What we first have to do is carry out step 1 for both reactants. So we're going to use our moles equals mass on molar mass equation for both the butane and the oxygen. We'll start with the butane. Moles of butane equals mass of butane over the molar mass of butane. We've got the mass of 5.78 grams, that's given in the question, and we can calculate very quickly, doing a side equation, the molar mass of butane, 4 times the molar mass of carbon times plus 10 times the molar mass of hydrogen gives us 58.122 grams per mole. And so we can plug that into that equation there, and we're going to get 0.0994 moles of butane from our 5.78 grams of butane. We can now carry out step 1 for oxygen. The moles of oxygen equals the mass of oxygen over the molar mass of oxygen. We've got 15 grams of oxygen, and the molar mass of the O2 molecule, which has 2 oxygen atoms, 2 times the molar mass of an oxygen atom, which is 2 times 15.9994. which equals 32.00 grams per mole. And we can substitute that into our equation and we get 0.469 moles of oxygen from our 15 grams of oxygen. So we've carried out step 1 twice and we've got 0.0994 moles of butane and 0.469 moles of oxygen. We can look at this number here and we can see that the moles of oxygen is significantly greater than the moles of butane. And so we might say, well, oxygen is there in excess and that butane is therefore the limiting reactant. Well, in this particular case, we would be wrong. That is not the case. What we have to remember is that the moles of O2 need to be 13:2 times the moles of butane, and that 13:2 ratio comes from the ratio of the stoichiometric coefficients, the 13 in front of the oxygen and the 2 in front of the butane. So 13:2 times the moles of butane actually equals 0.646 moles, and this number here is actually larger than the available amount of moles of oxygen. In other words, there's not enough oxygen present to react with the 0.0994 moles of butane. And so in this case, oxygen will be the limiting reactant. It's the reactant that's going to run out first. There'll be unused excess butane left over after this particular reaction. And it's important that we've identified oxygen as the limiting reactant because the moles of the product, the moles of the carbon dioxide in this case, are going to be now determined by the moles of limiting reactant, which is the moles of oxygen. Now, if you want a shortcut to determining which reactant is going to be the limiting reactant, you perform step 1 twice and we get these moles. You divide the moles of each substance by its own stoichiometric coefficient. So the moles of butane, 0.0994, divided by its own stoichiometric coefficient of 2. We get the moles of oxygen, 0.469, and we divide it by its own stoichiometric coefficient, which is 13 in this case. The values we get out, 0.0497 and 0.0361. This number here is the smaller of the two. Whichever number ends up being the smaller, that's the substance, that's the limiting reactant. So again, we find that oxygen is the limiting reactant and the moles of carbon dioxide are therefore going to be determined by the starting moles of oxygen. So in effect, we now ignore the step 1 calculation that we carried out for butane, and we're only interested in the step 1 calculation that we carried out for oxygen. We've now got to carry out, we've just done step 1, we've now got to carry out step 2 and then step 3. So in step 2, we are going to calculate the moles of carbon dioxide that are produced, and the moles of carbon dioxide, an expression for that, is 8 on 13 times the moles of oxygen. Remember, the moles of carbon dioxide are going to be determined by the starting moles of the limiting reactant, which is the moles of oxygen. The 8 on 13 comes from the ratio of the stoichiometric coefficients. That's the 8 divided by the 13, the stoichiometric coefficient of the substance you are trying to find information about, divided by the stoichiometric coefficient of the substance you have been given information about. 8 on 13 times the moles of oxygen, and we just calculated that in step 1 to be 0.469 moles, and 8 on 13 times 0.469 moles equals 0.289 moles. So now we have the moles of carbon dioxide that's produced, 0.289 moles. Step 3, we're now going to calculate the mass of carbon dioxide, and we use the rearranged form of our molar mass equation. Mass equals moles times molar mass. The mass of carbon dioxide will equal the 0.28 moles that we just calculated in step 2 times the molar mass of carbon dioxide, which we can calculate in this little side equation over here. Carbon dioxide has 1 carbon and 2 oxygens, so 1 times the molar mass of carbon plus 2 times the molar mass of oxygen. We get those values directly from the periodic table, and the molar mass for carbon dioxide being 44.09 grams per mole. We substitute that into this equation here, and we can get the mass of carbon dioxide to be 12.7 grams. So, in the first scenario, the combustion of butane, we had 5.78 grams of butane present in an excess of oxygen, and we produced 17.5 grams of carbon dioxide. In the next scenario, we had 5.78 grams of butane again, but this time we had a limited supply of oxygen, only 15.0 grams of oxygen, and in this scenario, we only produced 12.7 grams of carbon dioxide. And that's because the oxygen limited the reaction. The oxygen ran out first, there was some leftover unreacted butane, and less carbon dioxide was ultimately produced.